Okay, this video is part one in a series on electric power system stability, and ultimately we're going to write some code in future videos in C# to solve the power system stability problem, and we're going to be modeling some utility generators. Now, I'm not a big fan of just blindly following complicated equations, and generally when you see any tutorials or training on power system stability, there are pages and pages of very complicated equations. Instead, in this video, we're going to try and give a intuitive and conceptual and visual and graphical understanding of some very basic physical principles. And once you understand those, you can actually write your own equations, and you will have much better understanding of what the equations you see in the books really mean and what are the principles behind them. So I want to start out and talk about the equipment that we're going to be dealing with. And this is a very large electric utility generator. Down here is a guy walking down some stairs to give you an idea of the scope of how big this equipment is. This is a generator, and on the left-hand side, on the far end, you see the turbine. And here you see the generator itself, and then you've got the excitation system. So the important concept here is you have coming into the generator in the form of steam. In this case, you have mechanical power. You have steam coming into the turbine, and that steam pushes the turbine blades, and that causes this shaft to turn, which turns the generator, and the generator turning generates electricity. And ultimately, it gives electric power out of the machine onto the electric grid. So the most important concept here are size and mass and mechanical power going in and electrical power going out. A lot of what we do is going to focus on this mechanical power input and the electrical power output, and also the mass of this equipment. Now, to further explain some of the concepts behind the physics and the mass, this is a generator rotor, the part that gets turned by the turbine and generates the electricity. And you can see this is a large steel alloy mass that weighs many, many tens of tons. And you can see it's big. You can see these guys here about 5 or 6 foot in diameter. And this is rotating at probably 1,800 revolutions per minute or 3,600 revolutions per minute, which means about 30 times a second or 60 times a second, this thing makes a complete rotation. So it is spinning very fast, and you can imagine the inertia, the rotational inertia, that when this is spinning, this big mass spinning at that speed, it's very hard to change its speed, right? I mean, if this is spinning at, say, 60 revolutions per second, trying to stop that, just having a person try and stop that is impossible because it's so big and so massive. So you can see that with a big mass like this, when it's spinning, it's going to take a lot of energy to change its speed, either to speed it up or slow it down. So again, the physical concept there of mass and speed and inertia is very important to keep in mind as we go into this. Now, to take that into a smaller scale, here is a simple animation. Let's make believe it's you physically spinning a shaft that is the input to whatever this machine is. It's doing some work, and you are applying power on this rotating shaft to make this thing do work. Now, if you look at this, you can notice that it's a fairly constant speed. And this energy that he's putting in is being dissipated inside this machine because it's doing some work. Now, you can imagine that the power going into this is exactly equal to the power being dissipated, the energy being dissipated inside the machine, because it is rotating at a constant speed. Then power in is exactly equal to power being dissipated in the machine. Now, you can imagine, let's say he's pushing as hard as he can at a constant speed, and suddenly the shaft in this machine breaks. And suddenly you've got all this power, he's pushing hard as he can, and suddenly he's not pushing against anything because the shaft breaks. Well, what's going to happen? Suddenly he's going to speed up a lot, because he's no longer doing work, but he's putting a lot of energy into it. Now, conversely, if suddenly the work being done by this machine, maybe something breaks and causes this to be much more difficult to rotate, then suddenly, instead of a fixed speed, he's going to slow down because he's putting in constant power, but the power required to do the work has gone up, so he's going to slow down. So we have an intuitive understanding that the speed of this device is a function of how much power is going in and how much power is going out. If the power going in is a lot more than the power going out, then the speed is going to increase. Conversely, if the power going in is less than the power required, then it's going to slow down. That is an extremely important physical concept to understand when we're talking about stability and the response of electric utility generators on the system. So keep that basic concept in mind. Now, we can draw a graph of speed of this shaft versus time, and we can see that at this point, we'll pick a point right now where it's constant speed. We can see that the speed has been constant up to this point versus time, and that the power that the guy is putting in is equal to the power that the machine is dissipating, which means we have a constant speed. Okay, it's no different than you're driving your car on the highway and you have your foot on the accelerator at a constant position, which means the input to the engine in terms of fuel is constant. The power going in is equal to the power being dissipated by making you go at 60 or 70 miles an hour, okay? Now, this concept is no different whatsoever from that of a utility generator, where we have power going in terms of steam and power going out in terms of electricity the generator is generating. Okay, so exactly the same. It's been at a certain point in time, it's been going at a constant speed because the steam coming in, the power associated with that steam coming in is equal to the electric power generated and going out to the system. Now, like I said, if he is pushing at a constant power and suddenly the shaft breaks, the speed versus time graph is going to start changing. And suddenly you can see that the speed is going to increase and he's going to accelerate on this wheel, is going to accelerate the speed of the wheel because he's no longer doing the work, the same amount of work, and he's going to accelerate. So we have an intuitive understanding that the power input versus the power output directly affects the speed of the device, okay? Now, there is a difference between this guy and this generator. While they're doing the same thing, they're putting power in and power is coming out, they have different inertias, okay? This is a small guy, so if something changes, for example, if the required power to do the work here goes up, he doesn't have a lot of energy in reserve, so he is going to slow down quickly. Conversely, if the machine breaks, he is going to, the shaft is going to rotate a lot faster. Compared to a generator, which has a lot of inertia, it's a very big mass, any changes in speed are going to be very slow compared to what this guy has, all right? So if we drew graphs, we can say, okay, any changes of speed for the guy are going to be probably faster in the device relative to what's going to happen with the generator because it's got a much bigger mass, okay? Very important concepts: power in, power out, and inertia and mass. Okay, so based on this intuitive understanding, what do we know? Well, we know that big rotating stuff has big inertia, and conversely, small rotating stuff has smaller inertia, which means with big inertia, the faster it's spinning, the more energy it takes to stop it. And if the power in equals the power out, if they're balanced, then the speed isn't going to change. If the power in is greater than power out, speed will increase. And if power in is less than power out, the speed will decrease. We already saw that with the guy turning the crank. We also know that a change of speed is called acceleration or deceleration. And from what we saw with the guy with the crank, the change in speed or acceleration is proportional to the difference between the power in and power out. And we also said the acceleration is proportional or inversely proportional to inertia. So with big inertia objects, the acceleration is going to be slower and it's going to be less. Compared to small inertia objects, 1 over that is going to be a larger number. So a larger inertia means slower to accelerate or decelerate. So now that we've got that intuitive understanding, what's the problem we need to solve? Well, the big question is, how does a generator respond to changes, electrical changes in the power system? We need to know if something changes in the power system, is it going to be a minor disturbance and the generator can recover on its own? Or is it going to cause a major disturbance and the generator will go out of step, it'll go unstable and maybe trip off and we'll lose some generators. So it's important that we check for different disturbances that might occur on the power system, how the generators will respond. Will it be just a minor disturbance that they can recover from or not? So ultimately the goal is to predict and plot the generator response to system changes versus time. And here we've got a diagram, a chart, showing speed versus time for the generator. And here you can see it starts out as a constant speed and something happens and the speed increases for the generator. So we want our ultimate goal here is to be able to plot those responses of a generator to system changes. So now that we've got an intuitive understanding, let's look at the actual equations you'll see in the textbook and see that they're basically the same as what we just learned. Now here's a diagram of a simple nuclear power plant, and I've got a steam generator here that boils water and generates steam. And here I've got a turbine, and on the same shaft of that I've got a generator that's connected up to the power grid. And as you know, the steam comes into the turbine. That force of the steam, that mechanical input of the steam, turns the turbine blades, and that turns the shaft, which turns the generator, and the rotation of that generator causes electrical power to come out of the machine. So again, we've got this mechanical power input, electrical power output. We also said that the generator has a physical property based on the mass and the dimensions of the machine called inertia. How easy it is to change its speed based on the mass and the dimensions. Also, it has, as we showed before, a speed versus time value. So that's what this omega is, speed. It also has a synchronous speed, which is the normal speed, and in the US it's 60 hertz, and in Europe and other places it's 50 hertz. So that's the normal speed that the generator will rotate at. And here is one of the equations you'll see to describe the response of the machine, the speed versus power. And as you can see, this is right out of a textbook, but this is pretty much what we've already described. And what it says is the change in speed with time, which is basically this graph, change in speed with time, is equal to the mechanical power minus the electrical power. And there's also a constant here that has to do with the inertia and the speed. So this number right here, 2h over omega s, is a constant. It doesn't change throughout our simulation. So this simplifies things by making this a single constant. And this mechanical power input, generally we can assume that that stays constant, because in the time that we are evaluating the response of the generators, generally it's in a time in less than 5 or 10 seconds when a typical boiler on a power plant doesn't have time to respond, and it's fairly constant mechanical power input. So for this simulation, we're going to assume that this stays at a fixed value, say 1 per unit, and so this will be a constant just like these numbers will be a constant. So now, with those as constants, we can simplify the equation that says a constant times the rate of change of speed with time is equal to a constant of 1 minus the electrical power output, which basically says that the speed, the change in speed, is directly proportional to the electrical power output. A very simple statement that we can evaluate. So here's the complete equation the rate of change of speed with time is 1 minus electrical power over this constant. The change in speed is proportional to the difference between the input and output power and inversely proportional to inertia. So the big unknowns here are speed and electrical power. So we need to find the response, the speed versus the electrical power that the generator gives to the system. And that electrical power will change as the system changes. And that's what we need to find out. As the electrical system changes, the power going out of the machine changes. As you get faults or you lose load or you switch lines, this is going to change. This electrical power will change. So we need to see how the machine responds in terms of speed and other things. So as we start into this evaluation, what do we know? Well, we also know the conditions at the time before the disturbance. We said we're at a constant speed up until the point at which we're going to apply a disturbance. So since it's a constant speed, we know the mechanical power input equals the electrical power output up until this point. We also know the amount of the electrical power output. We can do that using a load flow. We talked about that in some previous videos where you analyze the steady state load flowing on the system and output by the generators. We can find that out very easily running a load flow that will tell us at the beginning point before we start the disturbance what the electrical power output is. So we know quite a bit here, and since we know that, we can now solve this equation. We know the electrical power output, we know this inertia, we know this A constant, so we know everything here on the right hand side, so we can solve this. So now you may look at this and step back and say, now wait a minute, how is this helping me solve what I need to know? I need a graph of generator speed or something else versus time. This doesn't tell me that, right? This is basically defining the slope of something. It has delta omega over delta t is a constant that basically defines a straight line with a slope equal to this. I plug in PE, H, A, and 1. I calculate that, just gives me a number, a constant, and that defines the slope of a straight line at this point where I calculated this PE. So at this dot right here, all I know is the slope of the curve of speed versus time, but I don't know the curve itself. So basically I've got a delta omega over delta t equals some constant, some number. And what I need is I need to make a graph of speed versus time. So how is this going to help me? Well, like I said, this is what you get from this number. You get a straight line with a delta omega and delta t. So how can I use this to figure out the speed versus time curve? Here is what I need. Here's the curve I need. So if you look at this, you might say, hey, wait a minute. I do have a straight line that is the same slope as the real curve at this point. And I notice here that if I go out a little bit, it kind of hugs the real curve. This straight line kind of matches the real curve out to a certain point, and then it diverges quite a bit. So you might say, well, I can use this straight line of this slope and go out just a little bit, and I will have at least a fairly good estimate of what the real curve is at this point. So if I can expand that a little bit, I can say, okay, we've got a delta t and a delta omega. I can just go out a little ways on this straight line defined by this value, this constant, this slope. I go out a little ways, and if it's a small enough distance, I will have a fairly good estimate of the actual curve. So then I can go out to here, get this new value of speed, and once I've got this new value of speed, that tells me the generator, and it gives me an estimate of the generator speed or position or angle at this point, and then I can go back and resolve my load flow for this new electrical power at this point using this estimate of generator position. And then I can go and resolve this, get a new constant that has a different slope at this point, and I can keep doing that. I can go out to the next one and the next one and keep going through that iteration to get estimates of this actual curve. So I'm not getting the actual curve itself, but if I use my head, I can get some really, really close and accurate estimates and just keep doing that iteration, resolving for the electrical power at the new position, and ultimately I will hopefully converge on a really good solution. So in the next video, we're going to talk about some of the ways, there are a number of ways to numerically do this, to come up with really close estimates, and from that you can get a really good estimate of the actual curve. And we're going to talk about that in the next video, talking about Euler's method and the Runge-Kutta method and some other numerical techniques that will help you solve for the stability of the machine. And I'll just briefly show you a C-sharp solution we will generate. And what I've got is a single machine, and I will go solve it. And here I've plotted out the resulting electrical power from the machine and also the angle of the machine. So we're going to generate this in the next video, show you how to do some numerical methods to come up with this. So I hope this helps. Take care. Have a good day.